Here we are back in the PLC Professor's Lab Development Center, and we are continuing with the lectures, the discussions for the lab projects for the advanced manual for RSLogix 5000, Studio 5000, and we're into languages. We just wrapped up ladder logic diagrams, did a fairly exhaustive discussion on it, and now we're going to do the first of two function block diagrams. I would say function block diagrams are more popular in the process control industry than the machine control. And one of the third languages, structured text, and we will also do sequential function charts, but you see a lot of structured text in machine control and in process control. So let's look at function block diagrams. Ladder logic diagrams, function block diagrams, structured text, and sequential function charts. This one is on function block diagrams, FBDs. This is one of the more fun languages to use because it flows the information a little smoother. When you look at ladder logic diagrams, you have to read quite a bit before you get the gist, before you get the essence of the process. But with function block diagrams, it's very easy to see the process. That's what makes these so popular. However, these are not good for basic machine functions. They're not necessarily good for math, but they are very good for process. So let's take a simple process. I just grabbed this one out of the air because I thought everyone can identify with this, even if you've never baked a single thing in your life. You've watched your mom do it or somebody do it, even if it was standing in a bakery watching some pretty young lady mix up ingredients. If you were going to sit down and organize the process for baking something, and I'm not sure what we're baking here, looks like it could be a cake or plain cookies or something, I don't know. The first step is you have to measure out the ingredients. You would measure out the flour, the sugar, the oil, the egg, probably egg powder, or it could be fresh eggs. Measure out the vanilla, the milk, and the water. Now each of these 7 little processes have their own uniqueness. You don't measure out flour the same way that you measure out oil. So each one of these little squares in this image represent a separate process. But this is the overall process. In the old days, when you measured out flour, you put it in a sifter, which was a cylinder, 10-cylinder device that had a screen on the bottom that was concave, and you had a handle you rotated bars around, and it pushed the flour through the screen and broke up any lumps. Sugar, typically, you would pour it out of the bag into a measuring cup. Same thing with the oil, the powdered egg. The vanilla would probably be a measuring spoon, and milk and water again would probably be in a measuring cup. But if you were actually considering this process for manufacturing, the powders would probably be Lawson weight feeders, and the liquids would come from tanks through valving, and you would even have to consider things like dribble from the valve, because when you shut the valve off, the liquid keeps flowing into wherever you're mixing the ingredients. However, you wouldn't really start anything until all the ingredients were ready. Now, if you were doing this in your kitchen, you would probably measure out most of these ingredients into the bowl to mix the ingredients. But in a factory, you would not. You would make sure that they were ready and available. If the ingredients are ready, then there's no reason to mix the ingredients until you can immediately transfer this perishable compound or mixture to the oven. So you'd want the oven ready. Then you would mix the ingredients. Once the ingredients were mixed, then you would pour them into racks. You could say cookie sheets, muffin pans, whatever you want to call it. Then you would load these racks into the oven, and there would be more of the process. My point here is each one of these squares is a separate process. The ingredients ready is probably the weakest in details of these squares here, these rectangles. It might be the permissive or the condition along with oven ready to trigger or initiate mixed ingredients. My point is, each one of these is a separate process. Measuring out the flour isn't just a bit you turn on to measure out the flour. You actually have a measuring process. So each one of these rectangles could be a sheet, and on the sheet you have all the individual steps. So you have this overall view, and it is linked together, and then you would have individual sheets. So think of your function block diagram as pages in a sketch pad. Each page is referred to as a sheet. In practice, use one sheet per device. Some of these processes may require more than one sheet because there may be many devices. Obviously, these examples right here don't follow with the baking process. I just wanted to show you a process or a sequence of processes that everyone could identify with. But you get the idea of breaking up your process into sheets. If you were going to sit down and write out the process before you programmed it, you would probably do it in block diagram form. This diagram was drawn in Visio, and in Visio you have a lot of latitude in how you connect these blocks. So you would sit down and start creating sheets. The sheet for oven ready has specific reference inputs that are going to come in to give you an output that says the oven's ready. Now it could be you have a 6-zone oven, meaning you have a metallic conveyor that goes all the way through this oven from the entrance to the exit. I've worked on ovens that were 300 foot long that had many more than 6 zones. So oven ready could be a very complex process all by itself based on having multiple zones ready. It may take more than one sheet just for the oven ready, because the controls for the oven, the gas controls or electric, are a process in themselves. Sheets help you organize your function blocks. The order of sheets does not affect the order that they execute in. When the routine executes, all of the sheets execute. You control a device by using these elements. An input reference is information in. A function block performs some function against that input reference. What comes out of the function block is either an indication of the quantity or quality or availability of the input reference. And there's many different types of function blocks. You could use a function block to indicate a state of the input reference and then use that along with other input references in another function block. As you see here, you have an input reference coming in the first function block. The output goes into a second function block along with 2 other input references. And then coming out, you have an output reference. Input references and output references come from outside the sheet, and the result, the output reference, goes to someplace outside of the sheet. Now that output reference may be used as an input reference in this sheet or some other sheet, but it comes from the tag database. So input reference and output references come from and to the tag database. An output wire connector is strictly a visual aid to tell you where it connects to another function block, either on this sheet or another sheet. So input and output wire connectors are pairs. Now I suppose you could have an output wire connector and no input wire connector someplace else, but I fail to see the purpose other than maybe it's strictly visual. And so you continue on through function blocks. Order of execution is defined by the wiring. So you see the flow of information here. Remember that an input reference is a piece of information. It's a value. And that value comes in through an input reference to a function block. It goes out. The same value doesn't go out, but the result of that function against that value goes out. So the connecting lines are called wires. A solid wire, of course, is a non-binary value, or rather to say it's a integer, single integer, double integer, floating point. A dash line is going to be a digital or binary wire. So dash lines have a state of 0 and 1. Solid lines can have a variety of values. The data flows from left to right through the blocks. And I suppose that you could do some sort of visual convolution to make it look like it's going from right to left. But the input references the output, like the output pin on the very first input reference there, it goes towards the right. So you would have to snake everything back to try to make it go the opposite direction. So we read English from left to right. These diagrams are from left to right. Again, I emphasize the advantage of function block diagrams is you see the flow of the information. Where each of these functions might be a separate rung in ladder logic diagram, you would have to look at the results in one rung, then pick up those results in other rungs to continue to follow the flow of data. As I said, wire symbols, solid line, single integer, integer, double integer, or real, and dashed is Boolean values, 0 or 1. Data latching. The data in this input reference, tag A, is latched for the duration of the routine's execution, even if it changes in the database, controller, or program scoped. So regardless of whether the tag is controller or program scoped, once this sheet starts to execute, the value of tag A stays the same until this sheet has been executed. In other words, you could use tag A in multiple locations in the sheet. So if tag A comes in as an input reference to block 1, and let's say come out of block 1 to block 2, and block 2 uses tag A again with the results from the function of block 1. Tag A going into the second block won't have a different value than it did going into the first. It's latched in. It's locked in for the duration of this execution. In this case, if the execution of block 1 changes the value of tag A, the value in the input reference does not change during the execution of routine. Because you're going to execute block 1 before block 2, if block 1 took tag A, changed the value, in other words, it created a new value based on tag A, and then had an output reference back to tag A as an input reference for this sheet will not change during the execution. The same applies in this instance. The value of tag A in the input reference does not change regardless of the results in block 1. This is something to keep in mind. In ladder logic, this is not true unless you buffer the inputs. You would have to buffer the values to hold them at one value for the duration of the execution of the ladder logic diagram routine. The order of execution is relative to the blocks that are wired together. The fact that the execution is not continuous in one group, the order within the group is determined by the connecting wires. The order of execution is appropriate within each group, and you see the order here: 1, 2, 3, 4, 5, 6. You might have thought that the first row executed first. So instead of 1, 3, 5, you would have expected 1, 2, 3, and then 4, 5, 6 on the bottom. So pay particular attention to this. Data loops. The input uses an output value that the block produced during the previous scan. In this case, the controller cannot determine which block to execute first. Data loops. One of the challenges with function block diagrams, remember that these sheets execute separate from each other. All the sheets execute, and the order is not necessarily considered because of the way they execute. Nonetheless, when you look at these two instances right here, in the first one, the input uses an output value that the block produced during the previous scan, With a single function block, the order of execution is irrelevant. It really doesn't matter. That feedback from the output of this block, that value will have been produced in the previous scan. In the bottom case, however, because there's multiple blocks to execute, the controller cannot determine which block to execute first because of the feedback loop. Therefore, you have to resolve the loop by specifying where the controller can assume data is available at the beginning of the controller scan. This loop is unresolved. This loop is resolved, and you can see that by the little double arrow on the input of one of the blocks. So when the controller sees this 3-block sequence, it assumes that the data is available for that block, so it executes that block first. Resolve one input only in the loop. Don't resolve both inputs. Multiple connections between 2 blocks. This is okay. This is okay where both are assumed, and this is not okay. This is confusing to the controller. So if you find yourself in a situation where you need to resolve a loop, or you need to specify which block to execute first, you can, and you have 2 inputs to the same block, they either both have to be specified or unspecified. Scan dependent logic, a 1 scan delay. Here we've created a 1 scan delay by assuming data is available in block 2. Therefore, it will execute block 2 before it executes block 1. Now I've got the numbers there to indicate the order of execution. So you could say that the second block is going to execute before the first block because you marked it as assume data available here. If you want to create a 1 scan delay, this is how you do it with function block diagram. Review these principles very carefully, otherwise you're going to dig a hole for yourself when you start using function block diagrams. When you indicate to the controller to assume data at the input of the second block, it uses the data output from the first block, but that was produced in the previous scan of the routine. When to use connectors. Connecting elements that are on different sheets is the most obvious use of connectors. When it is difficult to route around other wires and elements, you use connectors. In other words, you're on one sheet and you want to continue the process on that sheet, but you have to make a messy connection to go from the right side of the sheet all the way back to the left side to pick up another function block. Myself, I'm really particular about how my sheets look. I don't know why they function fine, whether they're ugly or pretty, but I use connectors specifically to keep the sheets more readable. You need to distribute data to several locations in the routine. So you may have an output connector in one of the strings of function blocks, and then many function block strings down below that that all use that same output value. Okay, here we have a function block that you did in lab. Now you're probably watching this before you did the lab, or maybe you've already done the lab and now you're watching all the function block diagram presentations. It really doesn't matter. So here's a function block diagram, and this is roughly its equivalent in ladder logic. So you can compare these two if you get a chance. Let's compare them logically. Here's our function block diagram. If the start push button, which is a push button, marked start push button, if it's true and the display enable switch is true. Now if you notice there, the state in which I grabbed this, the start push button is not true. Notice the 0 at the output end of the start push button input reference. However, if both of these are true, then start LED. In other words, turn on the output start LED, because the Boolean AND, ban_01, it's a 2-input AND. If the display enable switch is true and the start push button is true, then the output will be true, and that will turn on the start LED. If the start push button, then start the timer. And if the timer's timing, so you're looking at the timer timing bit coming out of the on-delay timer there, 01, then turn on the timer timing LED. If the timer's done, or latch, because that Boolean OR there, notice that the loop is resolved in input 2. So if the timer's done or the latch LED is true and not the reset push button, then turn on the latched LED. Now I put the not reset button right below and not reset button because the input reference is the reset push button, but we inverted it with a not because we want to see its opposite state in our logic. If we do the same thing in ladder logic, if start push button and delay or display enable switch, then start LED. If start push button and timer timing, then timer timing LED. If start push button, then enable the timer. If the timer's done or latched, then latch LED is on. Not reset push button, in order to make this text out the same as the function block diagram. If the reset push button it's a true if on, but if it's not, then you're not unlatching the bit, you're not resetting it. Linguistically it works out the same. Okay, that was languages of the Logix engine, a PLC professor presentation, function block diagrams. And this is a separate little presentation that is really kind of tacked onto the front of the first lab discussions for function block diagrams. Thank you for watching.